Hello, friends. We're going to start today with Amperes Law. Bum, bum, bum. So we're going to go on to the next major law of electrostatics. Hope all's going well out there. We are closing in on Thanksgiving, so in case I don't say it again at some other point, I hope you enjoy yourself a safe and happy, though probably unfortunately uh, rather small gathering for Thanksgiving. So with the situation we're in now, yeah, I think the smaller is probably the better. Is what we're just getting told. So um, anyways, as all the other holidays or whatever has happened since COVID started, it will be a strange thing, and at some point, hopefully, we'll look back on this and say, I'm glad that's over." I guess that's about the only thing I can think we would say. I kind of jumped in on that sentence without really knowing where I was going with it. But anyways, we're gonna get started with the electrostatic stuff. I'm sorry, the electrostatic stuff, the magnetostatic stuff. So we're gonna start talking about uh, s- funny word though. I mean, static. It's obviously not a static situation. It's better thought of as steady, right? Steady currents. So we're going to have a look at Ampere's law here. So let's get started. Um, Ampere's law, if I can take you all the way back to the beginning of, was it the beginning of the second day or something like that? Going through some of the electrostatic, I did it again. Going through the Maxwell equations, the electrodynamic laws, we happened upon one that looked like this. At least it looked partly like this. I'll say that. So this is going to involve, this is kind of our first circulation term. Okay, so we're going to talk about the circulation. C squared is the speed of light squared. Let's see. I have a little trouble fitting this on the screen if I'm writing that big. Well, that's okay. Okay, there we go. So C squared, circulation of B around C, that C is a curve, like a perimeter. I'll draw the picture in a sec. There's actually two terms involved in this one. This was equation number 4. You might remember, or you might not, but there was a d by dt term in this. But since this is a magnetostatic case, in other words, it's the case of constant currents, the d by dt term is going to vanish, and we're going to be left with the term of flux of, let's see if I can fit this all in here. And the answer is no. Flux of current density through a surface S, and we're going to divide by epsilon naught. Okay, so that's this is the part we're going to concentrate on now. This is the part, so let me just, this is the part of steady currents. So as I said, the d by dt term is going to vanish because we have no variations of anything right now. That will have to come at a later point. But right now, we're starting off with magnetic fields the way we started off with electric fields. And I hope that you're enjoying the parallels that kind of exist between the two. So here we are with Ampere's law, which is kind of going to play the magnetic role of Gauss's law. And finding the magnetic fields is going to be a situation of creating a loop for you to find the circulation of B, and look at the flux of current density through the loop surface and things like that. So here's the picture of what this looks like. So suppose I've got a large wire. All right. Let's see here. Suppose I've got a wire. Okay, so I've got a large wire. Okay. And there's current running through the wire in whatever distribution it is. And now around this, I don't like that. Let's not do that. There we go. So around this curve, this is going to be my curve C. Okay, that's my curve C right there. So I'm going to look at the circulation of B around C. I'm making a ridiculous drawing here because this is a fairly general thing. As we implement it, we're going to use circles. But just to let you know, so this is my curve C. And I'm going to look at the circulation of B around the perimeter of C. Okay. Now over here on the right side, I've got the flux of current density through S, and S is going to be the surface area that curve C has planar. It's the planar area surface, okay, inside here. I don't know if you can actually see my cursor moving there. So this is the area through which the current density is fluxing. Okay, so let's see if we can just draw that like this. So let's do that. So in comes some current, okay, like this. Okay, so this would be current density. All right, so that thing here, I'll put a surface, that is surface S. And then this is the current density, and the current density is J, which is current per area, like so. Okay, so so this is essentially the situation. So we can loop around our curve. So say we go around in some kind of counterclockwise manner here, go around. We can loop around, and what the essence of the law is saying is that the magnetic field that circulates around the wire or around the current is a result of how much current is going through the area. Okay, so it's very similar to Gauss's law in that sense, and it's divided by the same constant. You see, this is why I like epsilon naught. I don't use mu naught. You'll see this law written with just circulation of B around C equals mu naught times flux of current density. But I mean, that's fine. That's fine. That's the kind of the modern way of doing it. As I said, I like the parallels that epsilon naught has with this. This looks really a lot like Gauss's law, the way I've written it here. Okay, so if we find the flux of current density, and the current density in this case is J, through the area S, the surface area, so that's just going to be exactly what you think it's going to be. It's going to be a flux integral. Okay, so we're going to look at the flux of current density. So it's going to be an integral of J dot dA through the it's going to be a flux of current density through the surface S, okay? So if you like, you could rewrite this as integral I over A. And you have to be kind of careful. There's going to be a unit vector involved here. It's not typically kosher to put the vector sign on the current I, but we're going to do it anyways because I has a direction. All right, so it's like you can see that you're kind of integrating with area, and you're dividing by area. So this is kind of like enclosed. This is like the enclosed current in S. So this is very similar to the enclosed charge. Okay, so you say flux of current density, but it really gives you the enclosed current. Okay, so that's that part. And the circulation of B, computer screen for, oh, there we go. Okay, so the circulation of B, if you remember, we talked a little bit about this at the beginning of the semester, but that was a really long time ago. The circulation of B around C is, in essence, it's the tangential component of B as you go around. So if I were to kind of draw B here, suppose I had B and there's a B vector going off like this. What I'm going to do, and I'm going to take a ds, or yeah, I'm going to take a ds, which is that way. So I need the dot product. I'm asking how much of that B pointing vector is going around my curve, my curve C here. How much of that's going around? Didn't leave a whole lot of room here, but maybe, man, just moving this screen around takes an incredible amount of time, which you wouldn't have thought because this was supposed to be oh boy, what happened? Now I have no idea where I am. And that's interesting. Okay. Where? Ah, there we go. Okay. Now I recognize where we are. Okay, can I please just get a look at this? All right, I'm trying to blow this up here so I can look at a little piece of DS. You see there's an angle right in here between these two, B and DS. And so you're asking how much of this kind of oddly pointed B is going around curve C, right? It's picking out the tangent component. That's why the dot product's going to exist in this expression here. We're going to have B dot ds. And for those of you who like other expressions, this is akin to having the curl. This is you can't directly substitute because it changes things, because there's a theorem about how you do this, but this is related to the curl of B. Right, it's related to that curl of B. All right, so what we need to do is we've got to go all the way around curve C. Alrighty, so B dotted with ds, there's your circulation around C. So then mathematically, our entire thing here would look like circulation of B. So it looks like C squared multiplied by that. I enclosed divided by epsilon naught. Okay, so that's going to be the static version of Amperes law. Or I said static. I keep, no, it's the steady current. It's the steady current version. Let's get rid of this. Okay, so for steady currents. So it really plays the same role as Gauss's law does in electrostatics, and it's true for highly symmetric cases and nice infinite structures, or at least ones that you can approximate as nice infinite structures. So, so let's take a look. Oh, I guess what I want, one other thing I should probably note here is that I should just say, I talked about this. This sums the tangent component. Sums the tangent component of B times the perimeter. Okay. All right, that's what I meant to note there. And now let's take a look at some examples. There are problem steps which I can talk to you about. So in the course of doing this example, we'll investigate a few problem solving steps. Because just as Gauss's law, just as we had Gauss's law, we're going to have to draw an imaginary circle or a curve, right? Because we need to find the circulation of B around the curve. So I have to imagine a curve, and then I have to think about the current that's penetrating through that curve's area. So I got to think about, okay, so all right, what curve am I drawing? How much current is going through it? So you're going to run into a lot of the same thinking and mentality as we did with Gauss's law when we said, oh, I'm going to draw a Gaussian surface, right? And I'm going to think about how much charge is enclosed in there. And maybe I need to figure out how much charge is enclosed because there's a non-uniform charge density or something like that. And then I got to integrate that. But ultimately, your hope with Gauss's law was not to do that flux integral that was on the left side of E dot dA, right? Your hope was that you picked the Gaussian surface, which took care of all that stuff. So the same thing's going to be true with this and the circulation. If you pick the right curve to draw, which happens to be called an Amperean loop, okay, if you pick that right curve to draw, then you're not doing a circulation integral. Okay, probably the integral you're going to do is in the enclosed current, just like it was with Gauss's law finding the enclosed charge. Okay, so let's imagine that we have our first example here. Since Ampere's law is so good at long infinite current carrying structures, let's just do the simplest possible one, which is the example of the long straight wire. So this is the infinitely long straight wire. At least it seems infinitely long to us because we are ants on top of this wire, current carrying, I should say. Man, this thing, how come I can, don't ask. Okay, there we go. Current carrying wire. Okay, so a long straight current carrying wire. What is the magnetic field around this thing? Okay, this is a current carrying wire. We'll have the current going left to right, and it goes off in long enough distances left and right. So you might wonder, infinitely long for whom? Well, I kind of joked and said like an ant or something, but typically this is going to be a reasonably good approximation for almost, not every, but almost, well, let's say many situations. All right, this is going to be a pretty good approximation for many situations, because you're looking at small slices of an electric current, right? You take a small slice of this current and then look at the magnetic field around it. And if the wire goes off in a couple of, maybe a couple of centimeters that way and a couple of centimeters that way, that's probably pretty good, right? Because you're thinking about the creation of the magnetic field by the moving electrons. And gosh, it turns out electrons are pretty small. So almost anything is infinitely sized to those things. All right. So we need to, in this case, invent a curve that we can sum the circulation around. Okay. So we need to draw a curve so that we can have the curve do the same thing as the Gaussian surface did. So we need to not sum, but find to find the circulation beat and enclosed current. Okay, so this curve that we're going to draw, as I mentioned before, has a name. It's called an Amperian loop. This guy Ampere was kind of a important fellow in electrical stuff, as you can tell. He's got Ampere's law. He's got Amperian loops. He's got the unit ampere named after him. So I would have to say he did pretty good amount of work on the electrical side of things here. So in terms of problem solving steps, let's see if we can't go over to the side here. And these are going to look fairly similar to the Gauss ones that I wrote for you. Okay, problem solving. Okay, so I guess you could kind of say, once again, number 0, take a guess. What do you think the dependency of the field is going to look like? All right, this is how you build your intuition with regard to far field approximations, and then you look at that and you kind of reinforce it. So you take a guess at it and choose a loop. Circles are always, well, no, they're not always. They're usually reasonably good, but look at the symmetry. You didn't always choose spheres for Gaussian surfaces, right? Sometimes we chose little rectangular things, like little rectangular prisms, and sometimes we chose, other stuff like cylinders or things like that. So we're not always going to choose a circular loop. We might choose a rectangle or something like that, but okay. So we're going to choose a loop. We're going to need to evaluate what the enclosed current is. And that will be through the loop. Okay. As I said before, you're choosing loops in the same sense that you chose Gaussian surfaces, because you didn't really want to do that E dot dA flux integral. So choose a loop where you don't have to really do the B dot ds circulation integral. So check the dot product. Make the circulation of the B field, or I guess you can't make that do anything, but you can make the loop that you choose match the circulation of the B field. Okay. All right. Let's see, just a minute. Okay, so nice tea break there. Okay, so where were we here? Yes. All righty, so here we go. We're going to take a loop around the current wire here. Now this is going to be a very simple example, very kind of a beginning example. Okay. So just to illustrate, so we're going to choose a loop. In this case, what do we expect? Well, just as you wanted to get a feeling for the shape of the electric field, like it's radially outward from a positive charge, radially inwards for a negative charge. You know, if it's a plane, it looks like a, if you're close to a plane, an infinite plane, it's like a constant amount pointing away. So you kind of get these ideas. So the B field is curly, okay? It goes around. Now, if you remember the lab video where John had the really thick gauge copper wire going in and he deflected the compasses around it, it made a circle. So the thing about the long straight wires. Now, if you also remember this from the BIOS of R, right? We did DS cross R hat, and we came out with from a point up the top, it was coming out at us, right? So it circles, it circulates. So we're going to choose an Amperian loop centered on the wire with radius R. And we're going to evaluate, and this is the curve, this is our curve C. Okay, so we're going to evaluate the B dot ds around that thing, but we expect the B field to be exactly tangent to that at all points. So this takes care of our B dot ds integration. Okay, so if I were to draw, for example, if I were to draw suppose I looked at it from this view here, and I was looking down the wire that way. So the edge view, let's draw the edge view, would look like the current would be coming out of the page at you. Okay, and then my Amperian loop is like that. That's R. Okay, and what I'm expecting here there's a piece of DS, right? It would be that chunk, that small chunk of the circle that's tangent and becomes essentially a straight line as you take a small D differential part of it. And then you're going to find that the B field is curly all the way around it. It actually mimics that. Right? The B field is a circle. And I've drawn a start and an end to it, which is not correct. But I didn't really want to go right over the DS, but there you go. I just did it. There's no start and there's no end to the B field. It's a circle. So the loop that you choose, then you basically take care of the dot product, right? That was your point with getting the Gaussian surface, is to get rid of that dot product so you didn't have to worry about it. Well, same thing here. Choose a good Amperian loop, and then you don't have to worry about the dot product between B and DS, right? They're exactly in the same directions. It's a tangent field and it's a tangent DS, so we're all good. All right, so this leads to another kind of right-hand rule. Is this going to be right-hand rule? Is this like number 3 application of it? I think number 3. So for a long straight wire, this is actually kind of like 3 and 4 at the same time. Now, these are useful. This right-hand rule is freaking useful right here. This one and number 4, which I can tell you about in a sec, but this is really the one that you use. These are probably the ones you use the most. I don't even remember what. Oh, well, number 1 was for the force, so that matters. Okay, but look, right-hand rule number 3, to find the direction of a B field, and you want to know what direction is the B field around a straight piece of wire. Okay, look, look at your hand. Okay, look at your hand. You've got a curly piece of your hand, whoop, and you've got a straight piece. Okay, so just use those because I've got a straight wire and a curly field. Okay, so to find B around a long straight wire, put your thumb with the current. Your thumb goes with I, right? In this case, the I is pointing out of the page at me. How did I know the B field was curling around in a counterclockwise manner? Because if I point my thumb out with the current, then the handedness of my curly right hand fingers tells me, okay, it's going that way. All right, so fingers curl to show you which direction B is. Okay, freaking useful. So you can do this with any piece of wire. It doesn't even have to be a long straight wire. It can be any kind of piece of wire, and you want, even if it's a chunk of a loop, like even if I wanted that little piece of DS and I had a loop of wire going around this way, I can still do that. Forget what I said about the DS, but if I had a loop of wire, I could still do this type of right hand rule. So thumb with the current, and your fingers are curly and show the direction of the magnetic field. Why does this happen? Because it does. I mean, this is only a description of, well, why does the B field circulate that way? Because that's what we found. Right? That's the way it is, right? All we're trying to do is give a description of it. All right. So that's freaking useful. So I want to go back to this here. So number one, guess the answer. Well, we can't guess the answer. We don't really have that much of a knowledge of it, right? Do we think it's going to be a dipolar field? No, probably not. This isn't like a current loop. This doesn't look like a magnet, right? If it looks like a magnet, then it's a dipole field. This doesn't really look like a magnet. This is a long straight wire. So we can guess, I guess that it's not dipolar. How about that? We'll guess that, okay? So what's number? So that's 0. Guess. Choose a loop, done. Evaluate the enclosed current through the loop. That's great. So the enclosed current, I enclosed, well, I've got it all in there. So it's just equal to the current I, right? That's what this dot is right here. That's I. Okay, so there's my enclosed current. I enclosed everything. Evaluate the dot product. What's my next step here? Well, the screen doesn't move, so, and it's going to suddenly move a whole bunch. Wait, okay, check my dot product, then integrate. Okay. Now I got to take a look at integral around the curve C of B dot ds. Okay, so my curve, my dot product is taken care of because B and ds lined up. Check. All right, so that's going to become integral around curve of BDS. Because I've got a scalar product there, so I've got no vector part to that. So now B, I've chosen the Amperian loop to make B a constant value around the loop. So this is going to become B integral ds around the loop, and lo and behold, that's just going to become the integral around the loop, and that's the perimeter, the circumference of the loop, and 2 pi r. Okay, so there's going to be, that's going to be what you're looking for, right? That kind of thing. Oh, right, check the same boxes as you did with Gauss's. Dot product, okay, taken care of. Is the size of the field constant on the loop? Yes. Boom, comes out of the integral. Ding, here's your integral of the circumference of this loop. Now, if it's a rectangle, then you just have height and width and whatever, okay? But, or you have a circle, or you have whatever, right? It's just the circumference of the loop. So here is the final evaluation of the long straight wire via Amperes law. Come on, there we go. So now I put the whole thing together in Amperes law, and I got to remember all my constants. So I got a c squared integral b dot ds has become b 2 pi r. Okay, I enclosed is just I, and then there's an epsilon naught. Okay, and there we go. Solve for b. So take all that stuff on the left side, chuck it underneath on the right side, and it becomes I divided by 2 pi epsilon naught c squared r. Ding, there you go. Now, is there a situation where we could check this? Okay, look, number one is, hey, it's not a dipole field, so good, my guess was right. Doesn't it kind of remind you of the electric field of a long charged wire, a long straight charge wire, right? Falls off as 1 over r. Okay, so there's something similar. If we look back at the Biot-Savart result, right? We did an integration to find a finite sized length of current carrying wire, and then I extended the angles to be infinite ones. Let's see, do I still have that here? I don't know. I'm not sure if I want to spend the time looking back for that on this thing because it's so slow to move, but where is it? Ah, where we go. There's that disgusting garbage all the way down here. All right. So if theta 1 went to 0 and theta 2 went to 182, I over 4 pi epsilon naught c squared a, where a was the loop. Yep. So that canceled with that and became a 2. And it's 1 over the radius. Now I got to go back. Ah, yeah, look at that. So at least it checks with the Biot-Savart result, which is good. The last thing is, when you find the magnetic field, always make sure that you've drawn the direction of it somewhere, or that you somehow indicate this is a vector field, right? It's the same with the electric field. See, I drew my picture of B here, and it's going around in a counterclockwise as viewed from the right side of the wire, right? So how do I say, how am I going to say which way it's going? Well, I can always say that up top up here, it's coming out of the page, right? If I put my thumb with the current, my fingers show the curling. So it's coming out of the page at the top and going into the page at the bottom, which means that if I just draw it right here, it's coming out up here and going in down here. That's what B is doing, right? So yeah, make sure you have a picture or something. It's a vector field, so you got to have a direction. Make sure you have indicated the direction somehow with the picture, okay? All right, so that's the field outside a long straight wire whose radius is small compared with whatever. Now let's take a look at what happens inside the wire, where I can look at what if the radius of the wire is significant, right? What if I want to think about what's going on inside the wire? Okay, so now take the wire. So I'm going to have that same wire, and now I'm just going to look way closer at it. Okay, now I'm going to have a wire with current I distributed uniformly. There we go. Around, maybe I should say uniformly in the, this doesn't really work, in the area. Distributed uniformly on the area, maybe that would be better. There we go. All right, so what that means is that now I'm going to look really closely at that wire, and all of a sudden it looks like this big cylinder of copper, and there's a bunch of current flowing through it. Okay, so this is the current I. It's all right. that whole entire thing is the current. Okay. So now you can kind of start seeing, well, let's examine the current density, the flux of current density through an Amperian loop. Let's look at that. So in this case, the current is distributed uniformly on the area so that the current density is going to be a constant. Okay. Let's give the wire a radius A. All right. And suppose that let's see, what do I want to do here? All right, suppose I do the same thing. I'm going to look at it from this direction, and I'm going to pick an Amperian loop. Okay, so I'm going to pick an Amperian loop, mimic the symmetry, right? If I was outside this wire, which I just was, then I would have a circle. Well, I'm going to have a circle inside the wire too. And you want to make sure it's reasonably well centered. And I'm going to call my Amperian loop R. This is a horrible diagram, but it's supposed to be parallel with the face of the wire over there. It's supposed to be sliced the same way. It's not looking at it like coming out this way. Maybe I should foreshorten it a little bit. Well, I didn't. So if I look at it from this direction, then the edge view that I see would be, let's see, I'm going to turn it this way. So the current's all coming out at me. I've got, actually, never mind. I'm going to do this. So here's the wire. Okay. All the current. Oops, not uniformly distributed there. Okay. That's pretty good. Okay. So there's my current. Here's my Amperian loop. Like that. That's my radius R. This thing has radius A. Switch colors. Thank you. And the current is all, this is I. Okay, like that. All right, that's not going to switch color. All right, so now I want to do that thing where I asked last time in Gauss's law, I would say, find the electric field in all of space. Well, now we're going to do the same thing, find the magnetic field due to this in all of space. So that means I need to find it inside the wire and outside the wire. Well, we already did it outside the wire, right? So find B for the two regions for R less than A and R greater than A. But we already did that one where it's the B field outside. So that one's already set. Let's take a look at R less than A. So I'm not enclosing the full current anymore. Okay. Let's take a guess. When I thought about the charge, the wire of charge, and I thought about the charge density lambda, and we had the electric field, and outside it was a 1 over R electric field, and inside I think it was linear with it. It was an R field on the inside. Let's guess an R field for the magnetism on the inside. Let's guess that B inside is somehow proportional to R. Okay. Okay, so all right, so inside the wire. All right, so I already got my loop. I need to evaluate the enclosed current and check the dot product. So the enclosed current is going to be not the full I, right? But remember, I told you it was uniformly distributed over the area. So the enclosed current is going to be some amount of I, but ratioed by the areas, right? So I'm going to take the total I of the wire, divide by basically the capital A, which is the full area of the wire, and then multiply by pi r squared, which is the loop wire, which is the loop surface, right? So this is really, this thing here is pi a squared. That's the cross-sectional area. So it really looks like I divided by these things. We call I divided by the area, we call that the current density J. Okay, so that's the current density, and it's in amps per square meter if you like. All righty. So it's a ratio of that. It's the current density, and then it's just the piece that you do have. All right. So that should hopefully ring a bell with the enclosed charge, constant volume charge density in a sphere, and I'm only taking this much of it, right? So you'd say rho times the volume of the sphere. Same thing here. It's just the charge, the current density times the area. All right, so the B field and the dot product should be okay. My B field should be circulating. If I use my right-hand rule number 3, the current is coming out of the page at me, and I'm circulating around counterclockwise with the field. So the B should be going around like this. Okay, B field's going around like this. Okay, there's B. So my B dot ds turns out to be the same thing. All right, so that should turn out to be the same thing. So now I can hit it with Amperes law and go for the full thing. So I'm going to do c squared b2 pi r is going to equal the flux of current density. That would have been j dot dA, right? So maybe I should just go through and do a quick evaluation of that. I just did the ratio here, but that's okay because I is uniformly distributed. If it wasn't, then I would have to do that integral. All right. So let me just make sure that we're on the same page here. This is over the surface S, and it's a j dot dA flux integral of the current density. In this case, J is constant. So it turns into J times pi r squared, which is the area of my Amperian loop. And that's exactly what I'm going to get here. Now, if J was not a constant, if it was increasing with linear or decreasing somehow, if it was somehow a function of R, then you have to go in and do that integral, just like you had to do with the charge if the charge density was not uniform. Okay, we'll hit a couple of those too. But for right now, this is uniform. So we're going to do J times pi r squared here, and we're going to divide that whole shebang by epsilon naught. All right, so that's the flux of current density through the surface of the Amperian loop, and that's epsilon naught. So this is Ampere's law, so we're good to go. I'm going to get rid of the pi. I'm going to drop off an r, and I'm going to swing the 2 and the c squared underneath. So B, let's do this. Oh, come on. Come on. Let's start writing it here. B for r less than a is going to equal J. Wait, did I cancel that pi? I should have canceled the pi over there. I've got a 2 and a c squared and a j and an r. So I'm going to have j divided by 2 epsilon naught c squared r. That's going to be what the field looks like inside the wire. And then it transforms to a 1 over r on the outside. Okay. So this thing here is going to be just a line proportional to R. And then as it goes past the outside of the wire at A, then just because, like I said with Gauss's, it's often difficult to visually distinguish between a 1 over, like a reciprocal, 1 over R, a 1 over R squared, 1 over R cubed, e to the minus R. It's kind of hard to distinguish between any of those. So just nice to just put the dependence right on there. Oops, proportional to R. That's hopefully, that one I can distinguish. That's a straight line. Okay. So do the values match at the boundary? There's a question. So what's our value of the field out here at the boundary? Well, according to this, it should be JA over 2 pi over 2 epsilon naught C squared. So that's JA over 2 epsilon naught C squared. Let's take a look at the one where the field is coming from the other side, and we looked at it outside. So if I could make this, gosh, this is like maybe it's turned a little bit colder and the computer's slowing down even more. Oh man. Patience, patience. No. All right, so here we are. This is it. This doesn't look anything like it. But look what happened though. I had a J in the other expression. I've got an I in this expression. All right, so what do we want to do? Do we want to do it in terms of J or in terms of I? I guess we can do it in terms of J. We'll do this. So I is J times A divided by 2 pi epsilon naught C squared R. But R is now equal to A because we're at the boundary, all right? And this thing here has to be pi A squared because it's the entire current. All right, so that's going to knock a pi out. That's going to knock an A out, and I'm going to get a JA over 2, pi is gone, epsilon naught C squared, and the A is gone. So yeah, that's it. So it looks like these two values match at the boundary, JA over 2 epsilon naught C squared, which is good because you're coming at it from these two directions, and that means it's a continuous piecewise function, which is appropriate for a magnetic field. All right, so there's that. Okay. We have the same result coming from either direction. All right, that's good for now. I am just about done, and I'm sure you are too, and because doing this is not easy for anybody. So thanks for watching. Thanks for watching all the videos. It's getting down to that part of the semester now, so we'll do this for a little while, and then I think we'll have, let's see, we got this, and then we got to hit Faraday, and then we're gonna maybe do, I'm seeing a little bit, I can maybe sneak in a little bit on AC circuits. We'll see how we do. Well, anyways, thanks. I don't know what to say. If you've made it this far through the semester, keep going because you're almost there. So let's just get through this and we'll be done. All right. Happy day, folks.